Hey everyone, Mrs. Hanson, welcome back. Hope you had a little break from nomenclature in section 4.1, talking about naming straight chain alkanes, and we looked at a few examples of cycloalkanes. In this section, we're going to continue naming, but looking at a type of bicyclic compound. A bicyclic compound is one that contains two fused rings. And so, for instance, notice in this particular structure, we have a carbon, which we'll refer to as bridgehead carbons, that are actually fused into two different rings. And I'm going to color code these. The carbons that are in the first ring look to be like a 1, 2, 3, 4, 5, 6 membered ring. However, the carbons that maybe I could just highlight yellow here as well, they're also in part of a second ring fused to the first ring. And if you can envision that, these two bridgeheads are coming up to meet a carbon here and coming back down. So this is a bridge kind of coming up and back down to the bridgehead carbons. There are two bridgehead carbons in any two fused cyclic structures. This is also the same structure, just looking at it from a different vantage point. These are known as the bridgeheads. Those two bridgeheads are the carbons that are in both rings. The first ring these two bridgehead carbons are located in, we said, was a 6-membered cyclic structure. Notice that here is a cyclohexane. The two bridgehead carbons are also part of a 3-membered ring, 1, 2, 3-membered ring, and that is the second ring that's fused to the first. To name a bicyclic compound, which is going to take some practice, we include the prefix bicyclo in front of the parent name. So for instance, with this example, how many total carbons are in this structure? Again, we had 1, 2, 3, 4, 5, 6 carbons in the first ring, one more reaching up here to make a 7th carbon. So right now we could see that we would have a bicyclo. I'm going to leave a bracket and talk more about this in a moment. And then we have heptane as telling us that there are 7 carbons involved in a bicyclo. Now that means 2 fused rings. Let's talk about these parentheses next. Those parentheses are going to have numbers placed in them to let us know how many carbons connect to the bridgeheads. So let's count. I'm going to just maybe clean this up and change color. Let me use a red. Here's the two bridgeheads. Whoops, I wanted red, remember? And if I count 1, 2 carbons in this direction, and I can count 1, 2 carbons in the other direction. Oh, I went from this bridgehead, now I counted in this direction, and up here is a 1 carbon ring. So from the bridgehead, I counted all the carbons that brought me to the next bridgehead. So 1 bridgehead to the next in all directions from that starting original point. So 1 bridgehead, count to the next bridgehead. How many carbons separate them? When I count in this direction, I see 2 carbons separating the 2 bridgeheads. I count in this direction, I see 2 carbons separating the bridgeheads. When I count up, I count just 1 carbon separating the 2 bridgehead carbons. That's what we're going to place inside the bracket. And you want to number largest number first, then the in between, and then of course the smallest number. So here on the first side we had a 2. There were 2 carbons separating the 2 bridgeheads, counting to the right. There were also 2 carbons separating the 2 bridgeheads from the left, and only 1 carbon separating the 2 bridgeheads when I counted up. So this would look like 2.2.1. The largest number is placed first, and the smallest number is placed last. And if there's no point of difference, you're just going to repeat the number 2.2.1. Notice that the sum of these numbers is always 2 less than the parent name because the numbers do not include the bridgehead carbon. You're telling me how many carbons separate the 2 bridgeheads. So when I'm counting those numbers, those are numbers of separation. So a heptane, which has 7 members in the entire bicyclic structure, 2 of those are bridgeheads, and those are the carbons that are part of both cyclic structures. And that remaining 5 must be the placement of the carbons leading from one bridgehead to the next. So that's the kind of style we're going to practice in terms of naming bicyclic compounds. Those 2 carbons where the rings are fused are known as bridgeheads. They are highlighted here in green. Those carbons are involved in both rings that are fused together. We said there were 3 paths connecting those bridgeheads, and we count the number of carbons in each path to name the compound. For example, here I'm noticing I have a bridgehead carbon here and a bridgehead carbon here, and that is a 6-membered ring, just as we numbered on the previous page. But notice now, since this is a little different structure, let me try to redraw, and then from here to here is a bridgehead. So I'm going to just redraw that and kind of show, maybe in purple, there is 1 carbon here, 1 carbon here, and 2 plus 1. There's 3 carbons here, and I'm going to highlight the 2 bridgeheads right here. So these are known as bridgeheads. Those are the 2 carbons that are fused to both rings. So here's the second bridgehead. Those carbons are fused to both cyclic structures and are used in counting the total number of carbons in a ring. Counting the bridgeheads, we have 1, 2, 3, 4, 5, 6, and then in the second structure there's 1 more. So see how we say bicyclo, leave yourself room for the numbers inside a bracket, and you will have the total number of carbons in both cyclic structures as heptane. But to determine the numbering system within the brackets, remember that those are the number of carbons that separate the 2 bridgeheads. There we have it. So in one direction, we can see if I highlight perhaps, I'll highlight in yellow. In one direction from this bridgehead, 2, 3 carbons, and then we're back to the other bridgehead. So if the bridgeheads are highlighted in bright pink, which over the yellow makes red, but those are the bridgeheads, we can see by the yellow there's 1, 2, 3 carbons separating the 2 bridgeheads. That's the longest I see. So I can see that there's 3 carbons. It's the biggest number, so it's printed first. Then the other direction, I see just 1. And in the next direction, I also see just 1. So 3.1.1 is the numbering of the carbons that separate the 2 heads, the bridgeheads. So bicyclo, 3.1.1, heptane. Count the total number of carbons when you're finding the name for the cyclic structure. Yeah. We have the 2 bridgeheads here. There's 1, 2, 3, 4, 5, 6 carbons in the first ring. 1 more creates a total of 7 carbons, all combined to make 2 fused rings. Bicyclo, 2.2.1, heptane, telling me there's 2 carbons in 2 of the 3 directions and 1 carbon separating the bridgeheads. That's how we'll practice naming. So just to kind of practice step by step, we're counting the total number of carbons in the bicyclic structure. We'll find the 2 bridgehead carbons, and count the number of carbons along all 3 pathways from the bridgehead, making the largest number first, the smallest number last. So here is a structure. Draw it with me on your notes. We have a cyclobutane fused to a cyclopentane. So we have 2 cyclic rings fused together. The 2 bridgeheads are those 2 carbons that's involved in both rings. How many total carbons are in this ring? Well, let's count. There's 1, 2, 3, 4, 5, 6, 7 going the other direction. And carbon 1 and 5 are directly attached to each other. So again, you can see bicyclo, leave space for those numbers, heptane, the total number of carbons. And then when you work on the numbering, count the number of carbons that separate the 2 bridgeheads from all 3 directions. So here's the first bridgehead. I'm going to count this direction. There's 1, 2, 3 carbons that separated bridgehead carbon 1 and directly connected to that, bridgehead carbon 5. So that's where you see the 3. It is the longest pathway between the 2 bridgeheads. The second direction takes you left, and notice that there is 1, 2 carbons separating the bridgeheads when I travel left. The opposite direction is to go directly from carbon 1 to 5, and since that's a direct connection, there's no carbon separating the 2 bridgeheads. They attach directly to one another, so that's the 0. Bicyclo 3.2.0 heptane. This is an example that has some substituent branches as well, so that will become part of the name. So I see that I have an isopropyl branch coming off of the cyclopentane fused ring, and I have 2 methyl branches coming off of the cyclobutane fused ring. We want to work on naming the branches and now finding the number in the longest path that connects the bridgeheads first, making sure branches receive the lowest number possible. Number in the longest path that connects the bridgeheads. That longest path would be between carbon 5 and 1. A moment ago we called it 1 and 5. When we make a decision, should we count this clockwise or counterclockwise, that decision becomes very evident that this carbon, if it's labeled 1, has the branch called isopropyl at position 2. 2 is of lower number than if we had started here and we found it at carbon 4. So we have to number the longest pathway first and then decide to count clockwise or counterclockwise to make sure that the pathway gives you the lowest number on the first branch. Now we go around the longest first, and we found that at carbon 2 we had an isopropyl. When I got back to that original fuse, I went to the next longest, which in this direction went here. Right, so I had to go to the next longest. I wouldn't go straight down because that was the shortest pathway. So go to the next longest pathway, and then we have at carbon 7, 2 methyl groups. So here what we're saying, 7, 7 dimethyl. And we have that parent name we wrote up here, bicyclo 3.2.0 heptane. So put it all together alphabetically. I for isopropyl, M for the methyl, all part of that word, dimethyl bicyclo 3.2.0 heptane. You take practice, so let's try a few together. We're going to start naming the following bicyclic compounds. So I'm going to locate the bridgeheads. Those bridgeheads are involved in both rings that are fused together. I highlighted the bridgehead in purple. Let's count how many total carbons are involved in both rings. We have 1, 2, 3, 4, 5, 6, 7. So we have a cycloheptane is the first cyclic structure. And then carbon 1 to 5 connects with one more carbon, that's carbon 8. So I'm going to get my start here by saying bicyclo. Leave a room for the parentheses where we're going to count the number of carbons between the two bridgeheads. But I can see that a total number of 8 will be octane. All right, let's figure out these numbers for the brackets next. The two bridgeheads, I want to count how many carbons connect the bridgeheads. So let's use a yellow highlighter. We'll count 1, 2, 3 carbons when I went in this direction. Let's count the next direction. I'll count those in a green highlighter. There are 1, 2 carbons that connect in the left pathway. And if I count going up, there is the third pathway, and I'll highlight that carbon, let's say in blue, and I can see 1 carbon connecting the two bridgeheads there. So we order largest number first. There's 3 carbons separating the two bridgeheads when I went to the right pathway. When I used the left pathway, there were 2 carbons separating the two bridgeheads. And finally, when I went up, there was 1 carbon that separated the two bridgeheads. The total sum of the numbers in the brackets should be 2 less than the root word. So there's 6. 3 plus 2 plus 1 is 6. That leaves me the two bridgeheads from octane. So we have counted correctly. Now let's figure out the substituents. I see that I have 2 branches. Here I see a branch, and this is called an ethyl. And here I see a branch, and this is called a methyl. We want to number the longest ring first, the pathway that gives us the longest number first. So that was the 3. The question becomes, do we start at this bridgehead and count counterclockwise, or do we start at this bridgehead and count clockwise? Well, let's see where those substituents would end up. Carbon 1 is the first in that cyclic structure. Carbon 2, carbon 3, carbon 4, carbon 5, 6, and 7 would be up here. I missed one. That was apparent because I named it octane and ended up with only 7. So let me redraw. Here's carbon 1, 2, 3, 4, 5. Notice how I went around the longest pathway first. Found here is carbon 6, 7. That's the next longest pathway. And the shortest pathway will have carbon number 8. I want this to occur in this direction so that I have a 1 methyl, and at position 4 I would have an ethyl. Because if I numbered the opposite way, making carbon 1 this bridgehead and numbered clockwise, I would have ended up with substituents at 2 ethyl and 5 methyl. So clearly the 1, 4 is going to be of lower numbering than a 2, 5. So we're going to start in this direction when we number. And then we just alphabetize and we're going to put it all together. The alphabet says ethyl before methyl. So we write 4 ethyl, 1 methyl, bicyclo, brackets, 3.2.1, and finally the parent name, octane. These get long, don't they? They're not so tough. Let's try another practice. Practice will build for proficiency. Oh, this guy looks interesting. First thing is just look for the 2 bridgeheads, those carbons that are bonded to both cyclic structures. All right, so I just highlighted those in purple. Let's count the total number of carbons so that we can get the parent name of this bicyclic structure. I'll start at the first bridgehead. Here's carbon 1, 2, 3, 4, 5, 6, 7, 8. That's the first ring. Then I'll come up here, 9, 10. I count 10 total carbons involved in both rings. So I'll get my root word ready here, bicyclo. I'll leave room for those brackets and we'll fill those in a moment. And then I said 10 carbons, so it will have a decane parent name. Now that we counted the total number of carbons, let's go to work on the numbers for the brackets. How many carbons in each pathway separate the bridgeheads? So let's count going left because it looks the longest. Here's carbon 1, 2, 3, 4. Counting in the pathway to give me the greatest number, I see 4 carbons when I traveled left. Let's travel this direction next and we'll count those in green. There's 1, 2 carbons separating in the right direction, clockwise. And while I have the highlighter, we'll go up as well. The third pathway separating those 2 bridgeheads are also separated by 2 carbons. So we figured out the brackets. The yellows, there are 4 carbons in the counterclockwise pathway. There are 2 carbons heading clockwise and 2 more carbons heading up. So 4.2.2. Let's go to work on the substituent branches. So with those, I see that I have a methyl. Here is a methyl. And here's yet another methyl. When we begin numbering, we must start with the cyclic direction that gave us the biggest number, right? So there was 4 carbons. That longest pathway from the 2 bridgeheads gave us 4 carbons. So we are allowed to number from carbon 1, 2, 3, 4, 5, 6. That's the longest pathway first. And notice how I went in that clockwise direction there to hit the methyl at carbon 2. We'll then find carbon 7 and 8. I'm going to keep going to the next cyclic pathway. And I'm going to choose to go to the right there because there's substituents and I want those to have the lowest number. And then up here, I can simply continue my pathway with carbon 9, carbon 10. So at position 1, 7, 7, there were 3 methyl groups. All one word. 1, 7, 7, trimethyl bicyclo 4,2,2 decane. All one word there. Oh, this is fun. Sometimes these are challenging for me. I'm not a very good drawer, but we can sure give it a try. It says, let's draw this bicyclo structure. 2, 2, 3, 3, tetramethyl bicyclo 2.2.1 heptane. All right, so what should we do first? Well, I would suggest draw your 2 carbons as bridgeheads. Alrighty, so I wrote that down, kind of what to do first. Draw the 2 carbons, and I just did that, 1, 2. I know I'm going to need 7 carbons total, and there's the first 2. They're going to end up being bridgeheads. Now in one direction, it doesn't matter which, in one direction there's going to be 2 carbons separating the bridgeheads. So I'm going to just get that kind of down, and notice what I'm doing, I'm kind of making a connection that gives this a little 3-dimensional look. There is 2 carbons separating the 2 bridgeheads. I just chose to go right. I could go left. I have 3 pathways. It doesn't matter where. I've just got to pick a direction. And look at the other is going to be the same. So I've got 2 more carbons going in the next pathway, and I'll just connect them such like this. And then in the third pathway, there's 1 carbon between the 2 bridgeheads. So I'll do my best to connect them like this. Hey, that is not bad. There are a total of 7 carbons. So we have the heptane. We had the bicyclo telling us that 2 rings were fused. At carbon 2, there's 2 carbons separating the 2 bridgeheads in 2 of the 3 directions, and 1 carbon separating the 2 bridgeheads in the 3rd direction. So that's the parent there, the bicyclo 2.2.1 heptane. Now let's figure out this part. We've got 2, 2, 3, 3, and I could do this left or right. I'll just choose to do them here. 2, 2, there's some methyls. 3, 3. That's 2 more methyls for tetramethyl bicyclo 2.2.1 heptane. Cool. In this video, I'd also like to talk about constitutional isomers. Isomers, we know, are different structures that have the same molecular formula. Specifically, constitutional isomers are the same molecular formula, but different connectivity of the atoms. Isomers, they can be stereoisomers, which arrange their atoms in just a 3-dimensional way, stereoisomers, or we can have constitutional isomers. Now, when I say that constitutional isomers have the same molecular formula, but we just connect the atoms in a different way, we're breaking bonds and attaching them in a different order. Stereoisomers, which we'll study on in a little bit at the end of this chapter with cis-trans configuration, but it is also the entire topic of chapter 5, where we talk about stereochemistry in a chiral center and how it spins light around a carbon that has 4 unique attachments to it. So a little bit on stereochemistry at the end, but a whole lot of it coming next chapter. The focus here are called constitutional isomers. Let's say, for example, I have a 1, 2, 3, 4, 5, 6 carbon straight chain. We would call this hexane. In this compound, there are 6 carbons bonded in a straight line together. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. You knew that because H2N plus 2 is that general formula for an alkane, straight-chain alkane. 6 carbons gives us 14 hydrogens. But look over here. We have 1, 2, 3, 4, 5 carbons in the longest carbon chain. And off of carbon 2, we have a methyl. So practicing that nomenclature, 2-methylpentane, because we have a different order of attachment, we have completely different names. These molecules are completely different from each other. And yet, there's still 6 carbons in that structure. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are also 14 hydrogens. These compounds are called constitutional isomers. They share the same number and kind of elements. Both contain 6 carbons and 14 hydrogens, but the connectivity of those are very different from one another. When they have different names, they are different molecules, and they have different chemical and physical properties involved. Constitutional isomers share the same molecular formula, but they connect their atoms in a different order, leading to a unique name for the structures. As the number of carbons in this structure increase, the number of constitutional isomers skyrockets quickly. Let's say, for example, we have C3H8. One way we can arrange C3H8 is that a straight chain, 3 carbons just bonded in a row, and we know to label that propane. C3H8, propane. How else could we hook together 3 carbons and come up with a different structure? Well, no matter what I do with 3 carbons, I can try to figure out how to bond them, but it's only moving them as in terms of twisting a single bond. Notice that there's only one spatial arrangement to attach 3 carbons together. But what if I go to butane? This is a 4-carbon C4H10. One way of connecting butane, those 4 carbons, is a straight chain across. Or what if I did 3 carbons and a branch? That is a different name, isn't it? This would be 2-methylpropane, which is very different from the molecule called butane. Because they have different attachments, they have different names, they are different compounds, although they share the same molecular formula. There were 2 spatial arrangements for butane. Let's try C5H12. Notice that the most obvious is straight chain, just 5 carbons attached in a row together. That's one isomer. What if instead of 5 carbons, I had just 4 carbons in a row and placed one as a branch? So we've moved from pentane to 2-methylbutane. Those are unique names and therefore unique compounds, but they share the same molecular formula. Look what else we could do. We could do 3 carbons in a row and branch off of the center carbon. That's 5 carbons. It would be called 2,2-dimethylpropane. That's a third way of drawing 5 carbons and 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And you can see since carbon requires 4 bonds, every time we satisfy its tetravalent requirement, 4 bonds, we create the same formula, C5H12. But we found 3 different structural ways to arrange those 5 carbons. There are 3 constitutional isomers. And the game continues. 6 carbons, I can find 5 different ways of connecting 6 carbons, from straight chains to branches. There's 9 different ways to hook 7 carbons. And notice that as you increase the number of carbons, the number of constitutional isomers becomes quite large. Being able to recognize different structures is either being isomers or being the same compound. I think it just relies on 2 tests. One of them is to just think spatially and start flipping the structure around in your mind and decide, am I really just twisting the same molecule in space? Are all the single bonds superimposable upon the other molecule? Knowing that these single bonds or sigma bonds have complete freedom to move around, are they superimposable? Sometimes I'm spatially challenged, if you're like me, and thinking in 3 directions might not be as easy as doing step number 2. This is what I rely on. Name them. If they have the same IUPAC name, they're the same compound. If they're not the same name, but share the same molecular formula, same number of carbons and hydrogens, then they are indeed constitutional isomers. For example, I notice here we have a 5-carbon chain, so this is called pentane, if I could spell. Here, I have a 5-carb... Oh, Linda, counting. I made myself laugh. This is hexane all day long when you count to 6. So, more coffee. This we would have 2-methylpentane. These are not the same name, therefore they are constitutional isomers. 1, 2, 3, 4, 5. This would be 3-methylpentane. A unique name, therefore they are different compounds but share the same molecular formula, so they are called constitutional isomers. Then I can start branching into 4-carbon chains. Here I have 2,2-dimethylbutane. Shares the same molecular formula, but a different name, a constitutional isomer. This is also the longest chain as 4 carbons in a row, but now the methyl groups come off of carbon 2 and carbon 3. So the branching is a little different. 2,3 dimethylbutane. And still even here, the longest carbon chain is 5 carbons in a row, and off of carbon 3 is a methyl group. So even though it might look different on the page, it's exactly the same molecule, it's just twisted in space. And when I find that it has the same name, these two compounds are indeed the same, because I cannot name them with unique names. So therefore, they're not isomers, they're exactly the same compound. When you rotate that carbon from carbon 3 to carbon 4, you're just kind of looking at rotating this bond. You twist that bond up, and you really just see it's more obvious that those two compounds are the same. My trick is to name them and see if you get the same or is the name different. That allows us to make an informed decision if the compounds are isomers or not. And you'll have many practices on this. We can model a homework question from your skill builders. It says, are these constitutional isomers or are they the same molecule? That answer lies for me in just trying to find the longest carbon chain and see, do we have it? First of all, are there the same number of carbons? And are they connected in the same way? Those are key questions as we make our decision. All right, so I'm just going to start maybe here. 1, 2, 3, 4, 5 carbons in the longest chain. So this would be 2,3 dimethylpentane. Let's see, 1, 2, 3, 4, 5 carbons in the longest chain. And look, indeed, these have the same branches at carbon 2 and carbon 3. We see methyl groups coming off of a 5 carbon chain. So even though they look different on the page, it's just sigma bonds. These single bonds have just rotated in space, but they have the same name. Therefore, they are the same compound. They are not isomers. They're exactly the same compound, just twisted in space. Oh, let's try this. Interesting. I can see different connectivity already. How about you? Let's start numbering 1, 2, 3, 4, 5, 6, 7. That's one idea. 1, 2, 3, 4, 5, 6, 7. The blue gives me more branches, so I know that I'm going to number with the most branches. 1, 2, 3, 4, 5, 6, 7. That gives me 2 branches. At carbon number 4, we have a propyl. At carbon 3, we have a methyl of a 7 carbon chain. I just want to practice nomenclature. It's new to us. So this 3 carbon ring. So alphabetize, we have 3 methyl. And then at carbon 4, we have a propyl of a 7-membered chain. So there's its name. Let's try that skill again on the second structure. It looks like I'm going to need to start counting up here to get that first branch. 1, 2, 3, 4, 5, 6, 7. At carbon 2, there is a methyl. And at carbon 4, there's a propyl of a 7 carbon chain. These are different, aren't they? Because one of the branches has its methyl group coming off of number 3, and the other structure has its methyl group coming off of carbon 2. These aren't the same, so therefore they're constitutional isomers. They share the same molecular formula, and yet they connected their atoms in a different order. All right, that takes us to our next topic. So I'm going to stop the video here. We did some great work with nomenclature of straight chain, cyclo, bicyclo, and talked about constitutional isomers. And when you're ready, you'll come back to find talking about conformations and the relative stability of these alkanes. What are all the different ways to create stable configurations of branching?